Welcome to the Discrete Universe podcast. Today we're doing a deep dive into something so fundamental we often just take it for granted. Space itself.
Right. What is it, really?
Exactly.
Yeah.
You, our listener, probably think of space like, well, like an empty box, right? A
Mhm.
smooth, continuous void where everything happens.
That's the standard picture, definitely. The backdrop for physics.
But what if that's not the whole story? What if space, way down deep, isn't smooth at all? What if it's actually choppy, made of tiny discrete bits?
That's the core question we're tackling. Is space discrete, or is it continuous? And importantly, what's the difference between saying space is fundamentally discrete versus just, quantizing a space that we assume is continuous to begin with?
Okay, and our main guide for this exploration will be quantum geometry dynamics, QGD. This theory basically says space is fundamentally discrete.
It does. It posits these fundamental units, preons, interacting via a repulsive force called gravity, and that's what constitutes space. It's quite different from, say, general relativity or the standard model, where space-time is often treated as this smooth manifold, this continuum.
So the mission today, unpack these ideas, figure out QGD's argument for discrete space, and really nail down the difference between being discrete and being quantized. Get ready, this might bend your brain a little.
It's definitely a shift in perspective. But, the search for better foundations isn't new. Think about Hilbert's sixth problem, the call to axiomatize physics. It points to this need to really understand our basic assumptions.
Right, and even if we have successful theories like general relativity.
Exactly. They work incredibly well, we know that. But a new theory, like QGD, needs to explain why they work, reproduce all those successes, even if the underlying reason is totally different.
Precisely. The phenomena don't change, but the explanation for them might be built on a completely different foundation, like starting with discrete space instead of a continuum. Okay, so let's get into QGD. What's the absolute bedrock idea here about space?
The fundamental postulate, the starting point, is that space is discrete, period. It's made of these indivisible units called preons.
Preons minus.
Yes.
Yeah.
And they interact through a repulsive force, which QGD calls gravity. This force isn't something propagating through space. It's more like an instantaneous property between the preons.
Huh. Instantaneous.
Yeah. And critically, the dimensions we experience, three spatial dimensions, they aren't fundamental either. They emerge from the way these preons interact and arrange themselves.
Whoa, okay, so the preons aren't sitting in space.
Oh, no, that's the key shift. They are space. They don't exist in a pre-existing container. They constitute the container, if you like. The interactions between them define the geometry and dimensionality.
They are space. That really twists your usual intuition. So if space is made of these bits, what does that do to our idea of distance, like the distance between 2 points?
Good question. It leads to what QGD calls quantum-geometrical distance. Down at the scale of individual preons, or just a few of them, distance isn't quite the same as the Euclidean distance you learn about in school.
How so?
Well, think about basic geometry theorems. Pythagoras, for instance. A squared plus b squared equals c squared. That relies on a smooth, continuous space.
Right.
In QGD's quantum geometrical space, that theorem doesn't necessarily hold true at the scale of adjacent preons. The shortest path isn't necessarily a straight line in the Euclidean sense. It's defined by the connections and interactions between the preons.
So like hopping between stepping stones rather than drawing a line on paper?
That's actually a decent analogy, yeah. The path depends on the stones, the preons, and how they're arranged by gravity. The underlying geometry is different.
Okay, but we live in a world that looks pretty Euclidean, pretty smooth. Straight lines seem straight. Pythagoras works for building bridges. How do we get that space from these discrete preons?
Right, the emergence question. QGD addresses this with a theorem. Basically, it states that as you consider distances involving more and more preons, huge numbers of them, the difference between the quantum geometrical distance and the Euclidean distance gets smaller and smaller.
So it smooths out on average.
Exactly. Mathematically, QGD proposes that the limit of the ratio Euclidean distance divided by quantum geometrical distance approaches 1 as the number of preons involved, or the overall distance gets very large.
Like pixels on a screen. Up close you see the dots, but from far away it looks like a smooth image.
That's another good analogy. The macroscopic smoothness emerges from the microscopic discreteness. The Euclidean space we perceive isn't fundamental, it's an emergent property, a large-scale approximation.
Okay, this is a really crucial point then. QGD starts with discreteness. It's an axiom. How is this different from when physicists talk about, say, the Planck length or quantizing space?
Excellent question, because the terms can sound similar but mean very different things. QGD's discreteness is foundational, it's ontological. Space is fundamentally granular.
It's built in from the start.
Yes. Whereas many other approaches that talk about quantization, like those involving the Planck length, often start implicitly or explicitly with a continuous spacetime manifold, like in general relativity.
Okay.
And then they might introduce the Planck length as, say, a minimum measurable length, or they might try to mathematically impose some sort of granularity onto that pre-existing continuum. The quantization is kind of added on top.
Ah, I see. So it's like taking a smooth sheet of fabric and drawing a grid on it versus actually weaving the fabric from individual threads from the beginning.
That's a great way to put it. In QGD, the threads are the reality. The smooth fabric we perceive is the large-scale result. If space were fundamentally continuous, then quantizing it would be an extra step, an imposition. For QGD, the discreteness is the base reality, and the continuum is the approximation, the theorem that emerges.
So QGD is bottom-up, building space from discrete units. Other quantization ideas are often top-down, starting continuous and adding limits or grids.
Pretty much, yes. It's a fundamental difference in the starting point, in the assumed nature of reality at its deepest level.
Now, if space itself is made of these discrete preons, what does that imply for? Well, for matter, for particles.
Right. If space is discrete, then matter can't be continuous either, can it? It has to somehow fit into this discrete structure. QGD introduces another fundamental particle, the preon plus.
Ion plus. Okay, so we have minus and plus.
Yep. And preons plus are the fundamental constituents of matter. They are purely kinetic entities. They don't exist statically. They move by leaping from one preon to an adjacent one. Leaping. And a crucial rule is that a preon can only host one preon plus at any given instant. This leap mechanism, constrained by the preon structure, has profound implications.
Okay.
Well, for instance, QGD derives the constancy of the speed of light from this leaping mechanism and the properties of the quantum geometrical space formed by preons. It's not an axiom, but a consequence of the discrete structure.
Wow. Okay, so C emerges from the jumps.
In essence, yes. The maximum speed is set by the fundamental leap between adjacent preons. It also affects how QGD views gravity.
How so? General relativity is about space-time curvature.
QGD's gravity, derived from n-gravity interactions, isn't about curvature of a continuum. It proposes instantaneous variations in gravitational vectors. Because space is discrete, changes in the positions of matter particles, preons plus, instantly alter the n-gravity field throughout the preon network.
Instantaneous. Doesn't that violate things?
It sounds counterintuitive based on relativity, but in QGD's framework, gravity isn't propagating through space. It's a property of the interconnected preon network itself. It relates back to QGD's principle of strict causality, which helps define what's truly fundamental. It posits that only phenomena that don't require propagation are fundamental.
Okay. That's a lot to unpack there. What about infinities? Physics is often plagued by infinities in calculations. Does a discrete space help?
That's a major potential advantage, conceptually. If space and potentially time are fundamentally discrete, then infinities arising from dividing space infinitely or from point particles might just disappear. They wouldn't be features of the fundamental reality.
Because you can't divide a preon.
Exactly. There's a fundamental smallest unit. QGD even extends this to mathematics, suggesting that concepts like continuums and infinities in math might not be fundamental either, because mathematical objects and operations are ultimately products of physical processes carried out with finite resources in a discrete universe.
So even pure math might be grounded in physics.
That's the provocative idea QGD puts forward, yes.
Okay, let's circle back to this quantization term, just to be crystal clear. People hear quantum and quantization a lot. How can we ensure we're not confusing QGD's idea with, say, quantizing energy levels in an atom?
Right. It's about the object being discussed. When we quantize energy levels, we're saying that a system, like an electron in an atom, existing within a background space can only have certain discrete energy values. The energy is quantized.
But the space it's in is usually assumed continuous.
Typically, yes. When some theories talk about quantizing space or space-time quantization, they often mean imposing discrete properties onto an existing continuous space-time background, maybe for calculations or because of measurement limits like the Planck scale.
Like pixels on the smooth screen again.
Exactly, whereas QGD says the screen itself was always made of pixels. The fundamental reality, space itself, is inherently discrete. It's not about dividing something continuous, it's about starting with indivisible units. The ontological starting point is completely different.
Got it. Foundational discreteness versus imposed granularity.
That's the heart of the distinction.
Now, all this is a fascinating theoretical framework, but physics relies on testing ideas against reality. How does QGD, with its core axiom of discrete space, approach testability?
Absolutely crucial point. No matter how elegant a theory sounds, it has to stand up to the scientific method. That means providing descriptions, explanations, and crucially, testable predictions.
Predictions that are different from what current theories predict.
Ideally, yes. Unique predictions are the gold standard. QGD, being built on axioms like space discreteness, needs to derive consequences from those axioms that can be compared with observations or experiments.
So the argument for discrete space isn't just philosophical, it has to lead somewhere empirically.
Precisely. Theoretical arguments alone, like discreteness solves infinities, aren't sufficient. The framework built upon that discrete foundation must successfully describe known phenomena reproducing the successes of GR and the standard model, as we said, and hopefully predict new things. That's the ultimate test for QGD or any fundamental theory.
So as we've explored today, the idea that space might be fundamentally discrete, like QGD proposes, really paints a different universe than the smooth continuum we often imagine.
It's a radical shift, definitely. From space as a stage to space as the actors themselves, built from these preons.
And the key takeaway seems to be why it's discrete in QGD. It's not a quantization of something continuous. The discreteness is the starting point, the fundamental layer.
Exactly. The smooth space we perceive is the emergent phenomenon, the large-scale view.
This obviously has huge implications, not just for space, but as you mentioned, for matter, for gravity being potentially instantaneous, maybe even for the foundations of mathematics.
It touches on everything, really. If the structure of space itself is different, then everything that happens in space or is space needs reevaluation.
And while it's abstract, QGD aims to be a practical theory, reproducing known physics, and maybe explaining mysteries like dark energy, or offering new testable predictions down the line.
That has to be the goal, yes. Explanatory power and predictive power.
Well, the ultimate question, discrete or continuous, is still out there, a major frontier in physics. Hopefully this deep dive has given you, our listener, a clearer picture of what discrete space can mean, especially through the lens of QGD, and maybe spark some curiosity.
It's a journey into the very foundations, always worthwhile.
Indeed. Thank you for joining us on the Discrete Universe podcast. Until our next deep dive, keep questioning the nature of, well, everything. What if the answer isn't just about the stuff in the universe, but the nature of the room itself?